In this first lecture, we're all going to put together everything that this chapter has been about. We're going to be looking at how to predict what the major product is going to be for a substitution or an elimination. But not only that, be able to select the appropriate substitution mechanism or the appropriate elimination mechanism. So by the end of this, you should be able to just look at a reaction and figure out what the major product is, as well as draw what that major product is. So before we get into like, well, how do I decide? There's a few things that you need to look at in the reaction before you even start concerning yourself with what mechanism to choose. The first thing you want to look at is the substrate. And that's the thing that has the leaving group on it. So if we have a reaction, we have our reactants on the left. The substrate is here, and it's the thing that has the leaving group on it. And you want to look at the reagent, the other reactant, and that's usually above the reaction arrow. And that will kind of tell you, do you have a strong nucleophile or poor nucleophile, or do you have a strong base or weak base? And then the third thing you want to look at are the reaction conditions. And those are generally either above or below the reaction arrow. This things like solvent and temperature. And as I said, those are typically either above or below that reaction arrow there. And from that, you'll be able to predict the major product. So let's kind of get into how do we use this and what we've learned about nucleophilic substitution and beta elimination. So let's set up a little table here. Start with SN1, E1, SN2, and E2. Okay, and then we're going to look at the substrate and what conditions each substrate will react. So the first one is a methyl leaving group. So you have like, CH3X. And then we'll look at primary. So the leaving group is on a primary carbon. Then we'll look at secondary. And then along with secondary, we have like allylic and benzylic leaving groups. And those are all kind of very similar in their stability. So we're going to lump them all together, all three of those. And then finally, tertiary. All right, so when we look at the substrates, there's certain trends that we've already talked about. We're just going to kind of summarize them here in this table. For example, SN1 and E1 can never occur on methyl or primary leaving groups, simply because SN1, you cannot form a stable carbocation. So methyl carbocations, primary carbocations are not stable. So they're so unstable you can never form them. And so the same thing applies to E1 since they both involve carbocation mechanisms. With methyl, it's pretty simple. You can't do a beta elimination on a methyl because there's no beta hydrogen to pull off. So the only thing that a methyl carbon can do is sub SN2. Now with SN1, under most conditions, SN2 is the major product. And there's very unique conditions in which you'll be able to get E2 to occur. And that requires a strong, bulky base. And kind of the two that I want you to remember, I just use their acronyms. They're called DBU or DBN. And that's what these are up here. You don't need to worry about memorizing those names or structures. Just know the acronyms. And those are what we call non-nucleophilic bulky bases. So these are not nucleophiles. They can never be nucleophiles. And they act as bulky bases. And that will only do E2 on a primary leaving group. I say, what about tert butoxide? Because it's primary, tert butoxide will tend to do a lot more substitution than elimination. So if your goal is to do E2 on a primary leaving group, then use one of these two bulky bases. They're not nucleophilic at all. All right, so let's kind of bridge all of this together. Secondary and these allylic and benzylic is really a gray area and kind of the most difficult thing. Um, and so I'm going to split this up here because there's a noticeable difference between the quality of the reagent and doing SN1E1 or SN2 and E2. Remember that SN1 and E1 require weak nucleophiles for SN1 or weak bases for E1. Now, let's kind of highlight here how do you recognize a weak nucleophile base? Okay, so I'm going to go down here. What does a weak nucleophile or a weak base look like? These are typically things that are not charged. So, for example, water or an alcohol or an amine, those are kind of the most common weak nucleophiles and bases. And if you look at those, you're like, well, I can do SN1 or E1 with either of those. So like, how do I know what the major product is going to be between SN1 and E1 if, say, my leaving group is secondary? So this is where some of the conditions of the reactions come into play. So between SN1 and E1, E1 requires a lot of heat. A lot of times you'll see the delta symbol, or you'll see really, really high temperatures. Most reactions requires a little bit of heat at least, but like when I say heat, we're like heating them up to like reflux or to boiling. And it's the heat that's required to um, push the major product to be E1. And then with um, SN1, we use very little heat. There might be a little increase in temperature. I mean, we do it at room temperature or slightly above room temperature, but we don't, as I said before, typically E1 will require you to boil it or to reflux it. And SN1 occurs at much, much lower temperatures. Now, as you remember with SN2 and E2, SN2 requires strong nucleophiles or good nucleophiles. E2 requires strong bases. So how do you influence SN2 over E2? Well, with SN2, you want to pick something that is a strong nucleophile, but not a strong base. Okay, so what do those look like? Okay, well, strong nucleophile, weak base are things like X minus, the halides. Remember the halides like chlorine, bromine, and iodine? They come from strong acids. So the anions, chloride, iodide, bromide, are weak bases. RS minus. So if a thiol has been deprotonated, or even if it's still protonated, that's a very good nucleophile because it's a large atom. It's very highly polarizable. We talked about that term polarizability earlier. And then we can throw in CN minus into that mix as well. So all of those things make good nucleophiles, but are weak bases and influence SN2. Now, what about things that could go either way? Strong base, but also strong nucleophile. These could do both SN2 and E2. And what really governs it is what are the reaction conditions. So these are things like hydroxide. Hydroxide's a great nucleophile, but it's also a very strong base. OR minus, great nucleophiles, strong bases as well. Or even, I'll talk more about this in another chapter about how we make these, but these are called alkyne anions. Great nucleophiles, but they're also very strong bases. So how do I influence that? Well, let's again break this up here and go between heat. So with SN2, we want very little heat and polar aprotic solvents. So if I were using, say, hydroxide as a nucleophile, if I wanted it to be a nucleophile, I would use very little heat and probably use an aprotic solvent like acetone or DMSO. If I wanted hydroxide to be a base, then I just start heating it up. So these could go either way. It just depends on what temperature conditions you use. Now, one of the ways I can definitely influence a majority of E2 is to use a bulky base. Okay, so those are things like things that act as strong bases, but are not nucleophiles or they're very weak nucleophiles. These do exclusively E2 or mostly E2. So I've highlighted a few. We could use DBU, we could use DBN, we could use tert butoxide if it's not, if the substrate isn't primary. So for secondary and tertiary substrates. A weird one to kind of, I'm going to put in this list because it's not bulky at all, but it's not nucleophilic in this, in nucleophilic substitution is sodium hydride. H minus is not a nucleophile in nucleophilic substitution. So it's a really strong base in doing elimination. We will use hydride later in other chapters as a nucleophile, but not to do SN1 or SN2. Now, finally, let's address tertiary. All right, with tertiary here, we want weak nucleophiles and weak bases to do SN1 or E1. And again, the dividing line between that pretty much is no heat and heat. Now, I do want to put a little bit of caveat on SN1, is you can use strong nucleophiles, but it can't be basic at all. So you could use these things here. It's just not going to be as fast, but you can use them. Now, let's look at SN2. I'm going to get rid of these arrows here for a second. Now, I want to ask you a question and kind of yell it out at your computer screen. Can you do SN2 on a tertiary leaving group? And the answer you should be yelling out right now is a resounding no, because it's way too sterically hindered. So really the only option between SN2 and E2 is to use a strong base to promote E2. Now, I'm going to get into some examples. Before I do, I want to highlight a few important things about this. Don't forget about regiochemistry and stereochemistry. So remember that with SN2, that results, if the reaction's at a chiral center, it results in an inversion of configuration. SN1, again, if the reaction happens at a chiral center, that results in racemization or forming a racemic mixture. And in terms of regiochemistry, where we saw with like E1 and E2, E1, the favored product is the Zystev product, so the more substituted double bond, more stable product. E2, we could influence it. We could get the Zystev product by using a non-bulky base, or we could get the Hoffman product by using a bulky base. And remember that with E1 and E2, is if it's possible, the transalkene is favored over cis. Again, if possible. So what would a situation be where it wasn't possible? Well, remember in E2, the beta hydrogen that you're pulling off and the leaving group must be anti-periplanar. And sometimes that might result in having to rotate a single bond so that to get the hydrogen and leaving group anti-periplanar, and that would result in a cis double bond or the less stable double bond by maybe putting two big groups close to each other. So you have to remember to satisfy these conditions. Okay, so let's look at some examples. Okay, so how do we approach something like this? Well, first thing you're going to look at is the substrate. And what I mean by that is it methyl primary, secondary, or tertiary? So this is primary. And let's go up to the table here. If something is primary, then I only have two options. It could either be SN2 or E2. All right, so now I'm going to look at the other reagent that I'm given. So here I have sodium hydroxide. Now, a little tip here. With these ionic compounds, just ignore the cation and focus on the anion. So we have hydroxide here. And you need to, in your mind, label that as a strong or weak nucleophile base. So hydroxide is a strong base, strong nucleophile. And in terms of its base aspect, it's not bulky. So let's go up to our table here. And for something that's primary, it requires a strong bulky base. So since sodium hydroxide is not bulky, it is strong, but it's not bulky. Our major product is going to be SN2. Now that does not mean we won't get any E2. Chances are if we go into the lab and do this reaction, we'll probably get a lot of SN2 product, but we might get a little bit of E2. But most of the time and especially on your exam, I'm probably just going to be asking you for the major product. So that's the only one we're going to draw. We're going to substitute the bromine for the hydroxide because this undergoes an SN2 mechanism. So just be aware that on the exam, you're going to have problems, a number of problems like this, where I give you the reactants, you draw the product, and you need to indicate what mechanism it goes through. So either SN1, SN2, or E1 or E2, and draw the major product. Now, what if I had done something like this? We use the same substrate, but I give you the product here. And you're supposed to give me what is going to accomplish this. So the end result's the same, or the process we're going to go through is the same. This is primary. And so something for primary can either be SN2 or E2. But does this look like it's a substitution reaction? No, we got rid of things. We want an E2 reaction. So what kinds of things are going to promote E2 for a primary leaving group? Well, the only thing that can do that is a strong, bulky base. So I'm going to pick something like DBU or DBN. Note that tert butoxide, while we have called it a bulky base, will do more SN2 on a primary leaving group. All right, let's look at another example. Okay, so we're going to figure out first what mechanism we're going to go through. So identify your substrate. Well, the leaving group's on a tertiary carbon. And if you look at the table up above, that means SN1 could occur, E1, or E2. Remember, SN2 cannot occur on a tertiary leaving group. So now I'm going to look at the other reagent that's given. So sodium's plus, S is minus. I'm going to ignore the sodium and just focus on the S minus. So I need to identify what kind of base or nucleophile this is. So this S minus, go back up here to where we talked about it, is a strong nucleophile, weak base. So that's going to eliminate E2. That's also going to eliminate E1 because E1 requires um, weak nucleophiles or weak bases. So the predominant mechanism is going to be SN1. Now, even though if you look up above, SN1 does, favor poor nucleophiles or weak nucleophiles. That's okay. This is a strong nucleophile nonetheless, and we'll still do a substitution. So the major product will result from an SN1 mechanism. Okay, so in this next one, again, first thing you want to do is look at the substrate. This is tertiary. So what are our possibilities for that? Well, same as the last problem, SN1, E1, or E2. So we got a lot of choices. Let's look at the reagents and the conditions here. Um, Here we have a weak base, weak nucleophile, and we got heat. So this is going to eliminate E2. E2 requires strong, um, strong bases. Now, a weak base or weak nucleophile could favor SN1 or E1, and this is where the heat plays a role. The heat is going to favor E1. Now, let's draw out our products here because we have two potential beta hydrogens. Actually, I'll do those in a different color. We got a beta hydrogen there, and there's three beta hydrogens. I'll just draw them in on that methyl group. Do it like this. CH. So our two possible products are this or this. Now, which one is going to be the major product? So this is where it is important to remember regiochemistry. Since we know this is E1, E1 favors the xi-step product, the more stable alkene. And since this alkene is more substituted, it's going to be the major product. Sometimes it's helpful to draw out all the possibilities and then judge what your major product is going to be. Okay, now let's look at another type of problem. Let's say I give you something like this. And I say in the exam, E2 is favored. Draw the major product and explain why E2 and not SN2 is favored. All right, well, let's deal with the first aspect of that. Let's draw the major product. So again, we have an instance here where this base could pull off one or the other beta hydrogen. And we want the more stable product, the more stable alkene, which is the more substituted alkene. Now, why is it that E2 is favored and SN2 is not favored? Because if we just look at this, it's like, well, that's a secondary leaving group and there's no heat. So like, why didn't SN2 occur? Well, let's think about what SN2 requires. Okay, SN2 requires the least, the less sterics there are, the faster the reaction is going to go. Well, on this side here of the leaving group, there's a lot of steric bulk there. That's going to slow down the SN2 a whole lot. So the rate of SN2 is a lot less than E2 because of the steric, or what we call beta branching. If you don't remember that term, I highly recommend go back to the SN2 videos. So if there's a lot of steric bulk close to, but not necessarily on the carbon with the leaving group, that also slows down SN2. The other reason E2 is favored is that a tri-substituted alkene is formed. Remember in that decision between SN2 and E2, if you can make a tri or tetra substituted alkene, that's a whole lot more favored than SN2. Now I'm going to do the same substrate on the next example. Use the same reagent, but specify something else here. Okay, so now what does this added thing do to our choice of mechanism? Well, what is DMSO? Hopefully you're kind of saying it in your head. DMSO is a polar aprotic solvent. Well, what mechanism does that tend to favor? That favors SN2. So we're going to use this hydroxide as a nucleophile and do an SN2. Now, what's one thing I have to consider here? The reaction is happening at a chiral center. So remember that SN2 proceeds with an inversion of configuration. So the nucleophile will substitute from the opposite direction of the leaving group. All right, let's look at another pair of problems where just by changing the reagents, you can change the outcome of the reaction. So we look at something like this. Where's our leaving group? Well, our leaving group is on a tertiary carbon. So that means our possibilities are SN1, E1, or E2. Okay, so let's look at our reagents given here. Well, we have hydroxide. Again, I'm going to ignore the sodium. It's just a spectator ion. Sodium's a strong base, strong nucleophile. I'm sorry, hydroxide is a strong base, strong nucleophile. Now, what does that eliminate? SN1 and E1 right off the bat. So tertiary with a strong base just screams E2. Okay, so let's outline our possibilities here because we have alpha hydrogens here and alpha hydrogens here. So one of our products could be this. Another product could be this. There's one more possibility. You say, wait a second, there's only two beta hydrogens. Yep, we drew the pulling one beta hydrogen off or the other. But what about the orientation around this double bond right here? That is a different stereoisomer than this one. Because here, that big group on this side is cis to the hydrogen. Or we could say the two methyl groups are cis. And now here they're trans to each other. Which one of those, or I should actually, let's just put all together. Which of these three are the most stable products? Well, this is the Hoffman product. That's the least substituted alkene. So that's not a major product. And in this one, this group here is trans to a methyl. And here, this group is cis to a methyl. This situation is a lot more stable. So this is going to be our major product. So really E2 is kind of the trickiest one you have to look at because not only do you have to consider Hoffman versus Zeiss-Steff elimination, you also have to consider cis and trans isomers. Now I'm going to use the same exact substrate. But instead, I'm going to use water. So again, I'm dealing with a tertiary leaving group, so my possibilities are SN1, E1, and E2. So I'm going to look at the other reagent. So I'm given water. What is water? Well, water is a weak nucleophile. weak base. So that's going to eliminate E2 right off the bat. Now, is there a way I can decide between SN1 and E1? Look at the reaction conditions. I didn't draw any heat there, so we're going to assume SN1 is going to be the major product. So I'm going to replace the bromine with an OH. But note the reaction is happening at a chiral center. And for SN1, what happens to the stereochemistry at a chiral center? You get racemization. You end up with a racemic mixture. And what is a racemic mixture? It's a 50-50 mixture of enantiomers. I highly encourage you to work through some problems from your textbook. The only way that you're going to really master this is to practice these problems.